Hello. Yeah. Hi, I'm Kai. That's Fleming. Thanks for your serious interest into this workshop, and thanks to the organizers. We want to talk about the software SIRIUS and how to use that for the annotation of LC-MS-MS data. The workshop will basically start with a presentation about the software, and then we will do a live demo where you can follow and the steps on your laptop, and also feel free to ask questions if you have any problems. There was a new software release 2 weeks ago with SIRIUS 6, which changed a lot of things in the SIRIUS software. So on the one hand, it's nice because it's then an opportunity to tell you about new features and also for you to ask questions about the new software. On the other hand, let's see if we find some new bugs which we didn't fix in the new release. Will be exciting. So if you want to download the software and the demo data we prepared for the workshop, you can use this tiny URL. And there you also find the steps you have to do to log into the software. So in general, for all academics, the software is free, so you can also always log in with your university email account. And if that shouldn't work, you can always send an email, because sometimes some universities are not in our registry, so just send an email to info@bygiant.com, I think, or info@sirius.com, and then your university will be unlocked. Okay. So in general, SIRIUS is a software suite for the annotation of LC-MS-MS data. So the input data is LC-MS-MS data, and we annotate compounds in there with molecular formulas. We also annotate the fragment peaks of the MS-MS. We offer putative structure annotations and also compound classifications. Maybe a few words about the input data. So you can always provide just peak lists, so basically consisting of very basic information like what's the parent mass, what's the charge or the adduct of the spectrum, and then the MS1 and the MS2 spectra. These input format can be either in the MGF format, which I think is quite well known, or in our own internal MS format. But of course, for us, best format would be MCMLs or MCXMLs, or really the LCMS ones themselves, which we would then basically process in the software. So basically, then we offer a full suite of feature detection, adduct assignment, isotope grouping and detection, and so on. So basically, from your LCMS run, we will pick the features, and then you get a list of compounds where you have for each compound then an isotope pattern and the fragmentation patterns, which will be then analyzed with the software. As said, we also can import peak lists, and one way to use our software is to use mcmine for the preprocessing. Then there is a SIRIUS export function, mcmine, so you can do all your preprocessing in mcmine, export it into an MGF file, and then import that into SIRIUS. And the other way would be to directly process your MCML file with SIRIUS. So what's the difference? When should you do what? I would say the big advantage of mcmine is its interactivity. So if you want to interactively process your data and really look at each peak and decide what's the baseline and where do I put it, or where do I detect the peak and split the trace into peaks, then you should use mcmine, I would say, because it offers you a lot of parameters and so on. The downside of mcmine is that you have to provide a lot of parameters, while in SIRIUS the processing is fully automated. So if you just drag and drop the MCML file into SIRIUS, there's no interaction at all, there's no parameters you have to put in, so the complete processing is fully automated. So I would say if you want to invest time in your analysis and specify parameters because you think my workflow has very specific parameters I want to control, then use MC-MINE with the SIRIUS export. Otherwise, give just the SIRIUS preprocessing a chance because basically it contains all the functionality which is also in MC-MINE in the preprocessing, like adduct detection and so on. Right. So in the following, I just want to show you the basically the three annotation types you offer: molecular formula annotation, structure annotation, and component classification. So basically, these are all these tools which we have there in the middle are basically names of all these things, which is sometimes a bit confusing. We have SIRIUS as software suite, and then a lot of different tools with sometimes weird names. So the tool for the molecular formula annotation is SIRIUS, which is the same name as the software to make it even more confusing. And the idea of SIRIUS is basically annotate the molecular formula of the peaks. And I mean, the principle is quite simple. If you have a mass, to get, you know that in mass spectro or in chemistry, the mass of a molecular formula is mostly the mass of the atom summed up. So if I have here C15, H10O6, its mass is 15 times the mass of C, 10 times the mass of hydrogen, 6 times the mass of oxygen. And the idea of mass decomposition is basically to reverse this process. So give them a mass, enumerate all molecular formulas that have this mass. And unfortunately, usually you get multiple molecular formulas which have indistinguishable masses. And yeah, you have to distinguish them. So, like in this example, if you have the mass 286 with 10 millidalton mass deviation, you get these different molecular formulas. So you need some tool that decides which of these molecular formulas is the correct one, or at least the most likely one. And in SIRIUS, we use basically two sources of information for that. First, the isotope pattern. So basically, we simulate for each of these molecular formulas a theoretical isotope pattern and then compare the measured pattern with the simulated pattern. And the second source of information is the fragmentation pattern, where we compute a so-called fragmentation tree that best explains the data. And the fragmentation tree is basically a tree, which means you have nodes connected with edges, and each of these nodes corresponds to a peak in your spectrum. So in this case, for example, I have this node here, which is C10H8O3, and it basically belongs to this peak. So all green peaks and this blue peak here are basically peaks explained by the tree, and the black peaks here are are peaks which are not explained, so basically noise peaks, for example. And the edges in the tree corresponds to mass differences between peaks and basically to fragmentation reactions or hypothetical fragmentation reactions. Like in this case, we say that the mass difference between these peaks here corresponds to C4H2. So basically the neutral loss. And the general idea is that we first decompose the parent mass of a spectrum and enumerate all the molecular formulas that correspond to this mass. And for each of the molecular formulas, then we compute a fragmentation graph, which is we decompose all the peaks, which are subsets of this molecular formula, connect them with edges if two molecular formulas are subsets of each other. And then in this graph, we basically search for a subtree which maximizes the score based on some statistical model we developed. And we do so for each parent mass. And then hopefully the tree that has the best explanation for the data, so the highest score basically, is then also the correct one. So we use that basically then to rank the trees. And the score in the end is then added to the isotope pattern score and gives you the final score for the molecular formula. So that's just the molecular formula notation. One thing which is, I think, quite important is that this whole process is de novo, which means there is no database search involved, which is quite nice if you really have unknown unknowns, so structures which are not contained in any structure database yet, maybe even molecular formulas which are not contained in any database yet. they can all be analyzed with this process, because at no point we have any search in the database involved. The other thing is now structure annotation, like going from just a molecular formula to also a molecular structure. And the classical approach for that would be database search in a spectral library, like GNPS, MONA, MassBank, Matlin, NIST, for example. And of course, the problem here is that most spectral libraries are just too small, so you can only annotate a part of this data. And the alternative would be to use structured databases instead, like PubChem, Coconut, HMDB, which are usually much, much larger than the spectral libraries. So the idea in the tool CSIFingID, which is part of the SIRIUS suite, is basically to search in a structured database instead of a spectral library. And the way to do that is we first use a machine learning tool, CSIFingID, which predicts a molecular fingerprint from the mass spectrum and the fragmentation tree. And then we search this molecular fingerprint in the structured database to obtain the best molecular structure fitting to our data. And the molecular fingerprint is basically a vector of zeros and ones, where each position in this vector stands for some substructure. So basically we say, let's say this is a molecular structure, and each position corresponds to a substructure, and we just check if this substructure is contained in this molecule. If so, we write a 1 in here, otherwise we write a 0 in there. So you can think of a molecular fingerprint as a set of molecular structures, substructures that are contained in your compound. And it's basically a technique used in chemical databases a lot to compare compounds or to find compounds with certain substructures. And what CSIFingID is then doing, in the first version using a support vector machine. Nowadays we use a deep kernel learning, which is a combination of kernels, support vector machines, and deep learning to predict probabilities for each of these substructures. So essentially we say, for example, this substructure, what's the probability that I find this special kind of ring in my molecule based on the mass spectrum and the fragmentation tree. And after computing all these probabilities, okay, it's basically the workflow in detail, but I mean, look up the paper if you're interested how it works. I won't go into detail here. After predicting this fingerprint, you can then go in a structured database, and for each compound in there, you can compute the fingerprint. And compute means really it's a deterministic computation, because I can go over each entry here, look up the substructure, check if it's in the molecule, and write a 0 or 1 in there. And then I just compare basically this probabilistic vector, which I have predicted from the data, with these vectors from the database and rank them according to how well they fit. And with this trick, we can then search mass spectrum in a structured database. The problem is, of course, if we really have a large data set with thousands of measured compounds, and we predict or search in structured databases for each of these mass spectra, we will get a lot of wrong hits. I mean, how much compounds to be identified, that's really difficult to say, because it depends a lot on the data quality. Sometimes it's around 50%, sometimes it's just 30%. So a lot of your data will be just wrongly annotated. It's just as it is. And the question is now, how can we find out which part of my data is correctly annotated and which is probably wrongly annotated? And I mean, the most obvious thing would be just to use the score, which is offered by CSIFingID, saying that a good score is probably most likely correct and a bad score is most likely wrong. But we did some statistics, just plotted the scores of annotations which were correct and annotations were wrong, and found out that the scores are very similar. So you cannot say that a certain score is more likely to be correct or not. And it's not just a problem of CSIFingID. We find out that this is the case for basically all the annotation tools. And yeah, one of the reasons is also that the likelihood that the annotation is correct depends a lot on the database you search in. So we developed another tool called Cosmic, which not only considers the score, but also the database you search in and a lot of other information like data quality and so on. And in the end, gives you a scoring between 0 and 1, which tells you how likely it is that this annotation is correct or not. And if you just look at this score, you see basically the distribution of correct hits is much higher in the high region of between 0.6 and 1.0 compared to the incorrect hits. So it's much better than before. So you can now sort basically all your data by this cosmic confidence score, and hits with the highest score then the most likely hits in your result list which are correct. Yeah, here you see this basically. Let's say you have a lot of annotations for your spectra, and you sort them by the cosmic confidence score, and then hopefully the ones with the highest confidence are correct, and there will be still hits with low confidence which are correct, but that's as it is. Hopefully, and that's the idea here, is that there are very few compounds with high cosmic confidence score which are incorrect. So it's a little bit like FDRs and proteomics, just that it's not an FDR because that's an even harder problem to solve. But the idea is basically the same. Yeah, what is if the measured compound is not contained in the structured database? In this case, you can still use other information like compound classes, which we have a tool for called Canopus. And the idea is that we use a molecular fingerprint as input to predict which chemical class your spectra could belong to. Chemical classes like flavonoid glycosides or steroids and so on. And the special thing in Canopus is that it's really does this prediction based on your input data, not based on the database search. So, which means again, it's a de novo technique, so you can provide the input, the mass spectrum, and it doesn't matter if the compound which you have measured is contained in a structured database, the method will at least tell you it's flavonoid glycoside, for example. And the compound class ontology we use is from classifier and also from the natural product classifier. And in total, we predict around 2,500 compound classes. And you can use that to annotate your data set on a compound class level, which sometimes gives you already a lot of information, like instead of looking really into the compounds you annotate, just look at the data set as how many diterpenoids have I in my data set, or how many hydroxysteroids do I have here. And it might be already tell you a lot of things like the diversity of the compounds in certain chemical classes. And you can also use that, for example, to do statistical analysis like fold change analysis also just on a compound class level instead of a structure level. And you can also use that to annotate molecular networks, like which subnetwork, for example, corresponds to which chemical classes. And you will see quite often, for example, that you in certain subnetworks, like in GNPS, correspond then to, let's say, steroids and bile acids, or to flavonoids and isoflavonoids, or something like this. Yeah, to recap, basically you have these three annotation types, which are calculated by SIRIUS from LC-MS data. On the first level, the molecular formula. From the molecular formula with the fragmentation trees, then the predicted fingerprint with structured database hits, which are then also annotated with a cosmic confidence score to tell you if the hit is more likely correct or more likely incorrect, and also compound classes about the spectrum. Okay, as I told you, there's a new software release 2 weeks ago, so I just want to talk a little bit about the new features in 0.6. First, we have a completely reflowed preprocessing, which is now basically inspired by the preprocessing from Asari. which was published in Nature Communications 2023. The idea here is that if you provide a lot of samples, MCML files, then we basically search mask trace in the samples, recalibrate them, and then merge them all together. So like here, for example, this is one mask trace. You see there's a lot of, each color is basically one sample, and the black line here is the merge of all these samples. And the idea is now that the feature detection is done on these merged mask trace instead of the individual mask traces. So instead of basically doing feature detection on each sample separately and then align them, we first align everything based on the mask traces, then merge them, and then do feature detection. And the advantage is that this way you sometimes can separate features better, because in some sample it might look like there are two features, but if in all other samples there's only one feature, then it's probably just one feature, and this one sample is just a little bit noisy. On the other hand, if we have samples where sometimes it's only one feature and sometimes it's clearly two features, then if you look at the merged sample, you see, okay, this has to be two features, we have to split it here. So it should be more accurate than the preprocessing based on individual samples. Another new thing is that we now included spectral libraries into SIRIUS, because, I mean, that's still what people use most of the time. The advantage of spectral libraries is that it's, if you get a hit in a spectral library, I think it's a really strong indication your annotation is correct. So in most cases, CSI ID, because it's trained on public libraries, should give you already correct annotations if your spectrum is contained in a spectral library. But if you also get a spectral library match, then you know, okay, it's definitely correct hit. So it might be just a better indication. The other thing, of course, is that many people have in-house libraries, which we haven't trained on, and now you can put your in-house library into a SIRIUS tool and also search your compounds in your in-house library. The other thing is de novo structure generation, which is another thing you can do if your structure is not contained in the database. It's based on the MS Novelist method by Strauss et al. The idea in MS Novelist is basically you have a molecular fingerprint predicted, and we have some LSTM, some machine learning method, which is trained on structure DBs like PubChem or Coconut. And these LSTM predicts how a molecular structure for this molecular fingerprint could look like. And the special thing in MS Novelist and compared to other de novo tools is it doesn't try to find the correct structure, but it just gives you a structure candidate list. So you can think of MS Novelist like if there's no answer in the database, it generates a new database for you containing structures of this molecular formula which somehow agree with the predicted fingerprint. And in this structure candidate list, you can then search as you would search in PubChem or in Coconut. So, which means then you have basically the same scoring methods and the same features as a normal SIRIUS CSI search. So generate a structure candidate list, and then you get a ranked list where the top hit is most likely correct. If you try MS Novelist, you will see that quite often it even finds the correct answer just because it was trained on PubChem. It knows a lot of compounds already. However, I would say if you have a really new unknown structure which is totally different from the training data, it's rather unlikely that MS Novelist will find the correct answer, but it might give you just ideas how the correct answer could look like. So I think it's still worth trying it. Don't look at the top hit and say that's the correct one, but just look at the hits as suggestions how the structure could look like. We also simplify the computation workflow a little bit by first hiding a lot of options into some show at once settings dialog, and also it's now a little bit streamlined, like you don't have to do a Canopus prediction separately and so on. One thing which we'll show later is the API support. I don't know how many of you are interested in scripting. or are developing your own software tools, basically all features in SIRIUS are now available via REST API, which means if you develop tools or you just write scripts in R or Python or something, you can run everything directly from your script instead of using the UI or the command line tool in SIRIUS. And yeah, which also means you can extract all the results directly in your scripts. Yeah, what else? We improved the CSI finger ID method. It's now as a deep learning kernel-based method. We have a new confidence score, which also considers approximate search, but Fleming will show you this later. We refined the molecular fingerprint, and yeah, added more MS data. We now have the new NIST database in our training data. And we use now a new project space format. So for who of you is already using SIRIUS, you might find out that the new SIRIUS version is not longer directory structured, so you cannot go into the files directly and read them with your notepad. Instead, we now have a database, which might make things a little bit complicated in the beginning, but it's really makes development for us much easier. And it also makes the software a little bit faster. Yeah, before going to live demo, I just want to show a team behind SIRIUS. So Sebastian sitting there, who also give a talk tomorrow about SIRIUS and CSI Finger ID and all these other tools. And yeah, Fleming, and of course all my colleagues which are not here today. Yeah, and with that, I would say go to the live demo, which I think is an easier way to explain the software. And as said, if any one of you have questions, just directly raise your hand, and I can just go and help you.
Okay. Hello, also from my side. Oh, question already.
Yes, question. You said that you can directly import MZML files into SIRIUS software. Is that also true for DIA data?
So for DIA, I would use MS-Style because we need a convolution. You can import it, but it won't make sense, I would say.
Okay, welcome again. I'm Fleming Kretschmer, and I will guide you a little bit through the live demo part. As Kai said already, if you have any questions or if something doesn't work or if there's any problem, just raise your hand and we will try to solve the problem. First, I hope many of you have already downloaded all the data and the software. If not, here's the link again for everything is. Also, we will see that soon there's also the workshop account. So if you don't have created an account already, you can just use this account. I will make it a little bit larger so everybody can see it soon. And also one thing that is a little bit new, which wasn't there in the mail you probably received with all the preparation instructions, we have updated the data a little bit. And there's now a folder called new, which has 2 new files. It's not important if you haven't downloaded it. Oh, it has 3 files, but the important one is pretty much the Tomatidine SiriusDB. It's not important if you haven't downloaded it, but maybe if you can do it now, you can then follow along in one example I will show soon. Yeah, but first, if everybody has SIRIUS downloaded and extracted and installed, depending on your operating system, let's just start it up. So if you have the SIRIUS folder on Linux, it's mostly you just you get a zip file which you can extract, and in this folder you will have a SIRIUS folder, and there's a bin folder for the binary data, and there's just one SIRIUS executable which you can just run. I think on Windows, if you have installed it with a MSI file, you will just have like an icon on your desktop or in your start menu or somewhere. Okay, let's start up SIRIUS. It's also, maybe I can say this already, if you started on Linux, you often also get a terminal window which opens, and there you can, for example, see the log, everything that SIRIUS is doing. But this log you can also, I will show you soon in the main window. So let's make this a little bit bigger. Now we have SIRIUS open, and I hope it looks at least similar for everybody. Maybe just quick questions to everybody who has already used SIRIUS in the past, maybe another version. Oh, it's already really a lot of people. That's really nice. Has somebody already used SIRIUS 6 a little bit? Ah, even that, nice. Because it's only out for a few weeks, I think. Yeah, but especially for all the people who have used SIRIUS 5, for example, I will also highlight what has changed, and there are also quite a few changes which probably change everything a little bit, which you have been doing, which you maybe have to keep in mind. Yeah, but first, for all the people who don't know SIRIUS so well yet, this is how it looks like if you don't have any data inside. So you don't have much to look at, but you have some buttons, for example, to open up a project space. If you have already done some computations and saved them, you can load them up in this open button. You can, of course, save your workspace. But what is also important, you will see here in the menu bar, I think it's a little bit small, I hope everybody can see it, but you will see we are running SIRIUS 6, and we are already on some projects, which is, because it's on Linux, it's in the temporary location. So even if you just load in some data and you don't save it, it will be automatically saved in this temporary directory. But of course, at least on Linux, this will get deleted if you restart your system, so you should probably, if you have done some important computations, you should definitely save everything. Yeah, but you will also see, so in the middle, I will show this very soon, you have a button to compute stuff, you have a databases button, and a button to show running jobs. If we click on it now, there will not be anything there. As I said already, you have a log, which can show you something. For example, if you have loaded or if you try load in some data and you see that nothing is happening, or maybe not what you expect is happening, it's always a good idea to just look into this log window to see if there was maybe an error. Yeah, but this is also what you see in the terminal if you have this open. There are, of course, the settings. I don't think we have to explain here much. I think this is also new in SIRIUS 6. There's now a darks theme, if someone prefers that. But what is very important and what we all have to do now, if we click on this web service button, there's like a small red X. If you are not logged in or if something is wrong with your connection. I hope everything works now with a conference Wi-Fi. It's already taking a little long. But maybe while it's loading, I can already show you the information for logging in. So for people who are not logged in, let me make this a little bit bigger. Here at the bottom of the page, there's the workshop account. You can just use this email address and this password to log in, and then everything should work and you should have access to all the online services. Okay. It's still loading, which is not good. I will just cancel this and try to log in normally. So I will just copy-paste this to also use the workshop account. But if you have already made your own account, or if you were logged in already, this workshop account will only be temporary, so it will be disabled after the workshop. So if you have your own account, it's always good to just use that. Okay, now it works. I was afraid for a second. The web service tab is right now not working for me, but this is not a problem. Here you will just see if everything is available, if you are connected to the internet, and so on. Okay, now after a little bit of time, we also have this, and I can show it live. So here you have just some information about your connection. usually if you open this tab and you see you have some red crosses, you should check if everything is working. I think it's not happening very often, but sometimes it might be that the SIRIUS servers are down, in which case you would also see it here. Yeah, but here it looks very good. You can see here in the middle, worker instances are available for, and then you have all the services, and there are no worker instances unavailable for anything. So this looks very good. And now let's actually load in some data. I already gave you in the data to download, I gave you a pre-computed project space where the computations are already done. But before we do this, before we load this, let's just load some raw data, or pretty much raw data. In the folder there should be a mzml zip file. And if you have extracted it, you will have a folder, mzml, and it will contain some mzml files. And first we will just load some of these files. Sometimes it takes a little long, so let's just load like 4 files. Let's just drop them in. So what you can do, like what I'm doing now, you can just select some files and drag and drop it into the SIRIUS window, but you can also, I will explain soon. First I will explain this window. Now it's telling me that I inserted multiple LCMS runs, and it is asking me if I want to align them during the import, and yeah, in most cases you should just click on yes, and it is what Kai already explained, that for the feature finding we do aligning with everything that is measured or contained in the mzml files. So what you can also do, instead of using the drag and drop, you can just use this import button. For example, maybe for some reason drag and drop isn't working, you can just use this import button at the top. Okay, while it's aligning and doing everything, I just want to show you one quick thing, and that is, especially if you have you've measured some data and you try to load it into SIRIUS and nothing is happening, it's always a good idea to just look at your data first before doing anything else. So for the mzml files, it's unfortunately not very nice to look at it in a text editor, but it is definitely possible. And if you have, for example, MGF files, it's very easy to just open it in a text editor and look at everything. I will still show an example for the mzml file. Because it's 30 megabytes, it will also take a little bit to load it in a text editor, but it should look something like this. So everything is, in theory, human readable. And what I've highlighted here is that I've searched for value equals 2, which just shows me all the lines where some MS2 data is contained. And what is important for pretty much everything, we are using MS2 data for all the analysis parts, most of the analysis parts. So if you are using some, if you want to annotate your data with SIRIUS, you will want to make sure that you actually have MS2 data in the files you drag into SIRIUS.
Just one thing which I forgot. So with the new SIRIUS, we are also now import MS1 data. So that's very different from before, because in SIRIUS 5, if you drag and drop an LCMS run, then you only get compounds which have MSMS. Now we also import compounds which have no MSMS. Because, I mean, many people want to do then also quantization or statistics on the MS1 intensities. So all this stuff is now in there. But of course, so still, SIRIUS is mostly about MS annotation, so it doesn't make much sense to use SIRIUS if you have just MZML files without MSMS.
Okay. So now, I hope for everybody who's following along, there should now be something on the left side. On the left side, this is the compound list. Maybe for all the people who have used SIRIUS 5 and other SIRIUS versions, it has changed now a little bit because we are using these mzml files. There are now some names which have just been generated during the import. So these names will also, I think, be different when I later load in the pre-computed project space. I think if you import MGF files and if they have a feature name in these files, you will just see the feature name here, but here you will just have the IDs, and because it is quite new, we're also thinking about changing this name a little bit because it's often a little bit hard to just look at these numbers for feature IDs. And maybe just a tip, if you're using these numbers and want to find something, here the numbers start all with the same, so they are just an enumeration of the features pretty much. So if you want to find a specific compound, just use like the last 4 or 5 numbers, and you can just type it into the search bar if you are looking for a specific compound, and I will also very soon show you some examples where we do that. So now we have our compound list. You can see at the bottom that we have apparently 4,090 features here. It might vary for you depending on how many files you dragged into this SIRIUS window from the MZML files. And now I will just explain a few things before we have computed anything. What you can see already is that, and this is also new, next to the left of the compound name or to the feature name, you have now a small dot, a small circle, which here is mostly yellow, but there's also some dots which are green. I think if you don't have it on your laptop, it's a little bit hard to see on the small screen, but I will show you, I can show you directly what this corresponds to. This, for example, this green circle corresponds to the LCMS tab. And this you can see, you just click on LCMS and you will have this if you just import data, so you don't have to do any computations to see this tab. And there you can look at the peak shape and everything. And what you will also have here, you will have in the bottom, you will have the files which we just imported. And if you hover over it, you will see the actual peak or the actual trace which corresponds to this specific file, which I'm highlighting now. And on the right side, and this is where this green circle comes in, we have a traffic light system to show how good the quality is. We have some things we determine here. So for example, how good is the peak quality, how well was the alignment performed, how good is the isotope pattern, and so on. And maybe I can find a little bit better example to show this, because what you will see, let me just go a little bit down, because this is also something, if you just load in some data, all your compounds will be ordered by retention time by default. So let me just go out of the void volume somewhere here. Yeah, okay, now this looks interesting. Let me show, yeah, this is a good example. Now you will see the peak, but you will actually see like a gray box here. And if you zoom on this gray box, I will do it soon, this is actually what the feature corresponds to. So this is actually the peak of the feature which we are looking at here. Okay. Now that we have seen everything, at least without computing something, maybe one thing we can look at before we do computations is in the formula screen you can already look at your spectra. So you can look at the MS1 spectrum, for example. Often you will see the isotope pattern here, or you can see some adducts, for example. You can also look at the MS2 spectrum or spectra. What is important here is that by default we show a merged MS2 spectrum. And if you have, for example, measured the same compound with different collision energies, the merged spectra will look different than just the spectrum for the one collision energy, and you would be able to select multiple or the different collision energies of the spectrum here in this box. But because in this example we only have one collision energy, we will only see this for the spectrum. I will show you also the spectra view a little bit in more detail when we have actually done some computations. Yeah, you will see for everything, for all the tabs, there is not much because nothing has been computed yet. So let's try to do some computations. Especially if you now try to follow along and something doesn't work, it's not bad at all, because we will just soon load in a pre-computed project space so that we also have exactly the same data to look at, and so we don't have to wait for computations. But let's show how it looks like, what you would normally do. So maybe I can show this first a little bit. So what you might even want to do before you do any computations is filter everything you have imported. And to do filtering, of course, I said it already, you can type something in the search field, for example, the name of a feature, but you could also, for example, type a mass to get something. For example, to get the first compound, and could also just type in 139 and point, and I would get all the compounds which have a mass of 139. But let's do actually some more useful filtering. Something you might want to do in the beginning is, I showed you already in this LCMS view, you have this traffic light system for the quality. And we now you're also able to filter out features which have a very bad quality. So I will explain this in more detail very soon. But what you can see in the middle is this quality filter. And here, I think this, if we go from right to left, this column which says good is the green circle, then decent would be yellow, bad would be the red circle, and gray would be the lowest, I hope. Yeah, okay. Yeah. And what is often a good idea, the lowest is really something which we are thinking about of just kicking out. So this is really something where, for example, there's not much measured or something is very wrong with your data. So it might be a good idea, before you do any computations, to just throw all of these features out anyways. And to do this, you can, for example, just deselect this checkbox here for the lowest overall quality. Now we have not selected anything else, and we will just click on apply. Or what we could also do, there's also a checkbox here at the bottom which says delete all non-matching compounds. If we just apply this filter, this just means that we are filtering our view, but everything that doesn't match our filter will still be in our project space. But if we want to kick it out completely, if we want to delete it from our project space, we can tick this checkbox to really delete it. But let's not do this, let's just do apply here, and you will see now all the gray boxes will be gone.
Maybe just a few words about these lowest quality. So in principle, SIRIUS is detecting all the features, also things which are clearly not the real peak in the beginning. And I mean, usually you would just then kick them out, like first pick all the features, make the alignment, and then decide that a lot of this stuff is probably noise. And currently we don't remove them, so they are just flagged as gray, basically gray boxes, or as lowest quality, and you can interpret this as to remove. So maybe in some later update we will remove them automatically, or we just give the user the choice if you want to remove them, but it's usually a good idea to not look into these gray features. They are really usually noise. And it's just this traffic light, red, yellow, and green, where we say red, we cannot decide if it's noise or not. It looks really bad, but it could be still a real feature. So that's the three type of compounds you should look at.
Okay, now let's try to do some computations. What you will notice, you can just click on any compound and then right-click. You will have a context menu, and there will be also an option to compute if you want to compute something for only a single feature. Just to show this first, because this will look a little bit different than what I will show you soon, which is when you select multiple compounds or just click the compute all button at the top. So this would be only for one compound, but we'll also do this in one example. But now I want to show you how it looks for many compounds. Just if someone also wants to actually do computations, would be probably a good idea to not click on the compute all, because it can take a little bit if you don't want to wait, and just select, I don't know, 4 or 5 features here. You can just use your normal shortcuts, which you would also use in the file explorer. For example, you can shift select or control select to select multiple compounds. You can even hit Control A to select everything. And now let's again click on, let's right click and click on compute. And as I said, this looks a little bit different than what we just saw for one compound. For example, now we will see here this zodiac button, which was not there when we just hit this on one compound, on one feature. Yeah, but just an overview. Kai already showed a slide that it's now a little bit, we now have pretty much two modes. We have, this is the basic mode or the normal mode, which most of the settings you might want to modify. Yeah, question? Sorry, I couldn't understand. Have you selected one compound or multiple? Multiple. Yeah, you should select multiple or click on the compute all. Yeah, this is exactly what I meant, because Zodiac, I can show this now already. If we click on Zodiac, it will show us a box to confirm that we really want to use it, because it is meant if we have a complete data set, if we have much data measured, it is designed, or it was developed to improve the formula annotation, and it doesn't make sense if you just have one compound or if you have like two commas or something.
So in principle, you can think of it like it's doing some kind of molecular networking and then tries to annotate networks in a way that they are consistent to each other. So it's a re-ranking method which only makes sense if you apply it on the complete data set. It doesn't make sense to do that for 5 compounds or something. So you would run it on a complete ACMS run with, let's say 1,000 compounds or something, and then it will improve the ranking significantly.
So we had this warning. Let's just click no for now and explain everything in order. So all the tools. Question?
When you apply the filter,
Yeah.
you will remove all the data with that data quality, but it will not able to analyze again, or it will be removed from the workspace.
Yeah, I can. I can show it again. There's pretty much, or there's 2 things you can do if you are in this filter window. You can either, so I can show it a little bit more. It's unfortunately not very big, but there's an option at the very bottom which says delete all non-matching compounds. And if this is enabled, you will delete everything which is not in your view. But normally, so the default is to not enable this checkbox, and then stuff will not be deleted from your project space. You will be able to analyze it later on. But if we enable this checkbox, it will be deleted from your project space, but of course, the data will not be deleted, so the MZML will not be affected. But the project space can be a little bit smaller, so it can make sense if you... I think it also happens now that the project spaces can get a little bit big, so maybe if you want to share your project space and you don't care about many compounds, you can just really delete them. I think it's even possible if we just right-click on like a specific compound. There's also an option to just delete it. So you can also select some compounds and delete them completely from the project space. And as I said already, so we are now in this temporary project location. So everything we do will be automatically saved to this project location. Okay, back to the compute dialog. So again, to get this, Mark, question? Mm-hmm.
Don't choose any adult of the database. Means all of them are included, correct?
You mean the LCMS tab?
No, that's with filtering.
Okay. The list on the left.
On the top at the blue filter tab.
Yeah.
And then in the adult or the database, if you don't click anything, it means they're already included. Am I correct?
Yeah. It's so this is filtering, meaning that now everything is included without any boxes ticked. Exactly. Yeah. I will also show an example soon how you can utilize this, for example, for adducts or for structured databases. Yeah. I can also show this already, and which will be very important probably because maybe you have messed something up here or selected something you didn't want to select. At the bottom left, there's a reset button which turns everything to the normal settings where you don't apply any filtering. Also, what is good to know is this button will be blue, this filtering button, if we have applied some kind of filtering. So especially if we are later going to some specific examples and you don't see the feature, it might be that you just have this filter enabled still. Okay, just to walk you through a little bit of the computation dialogues. So this will be something you will probably look at quite often if you use SIRIUS. So it's important to know at least in general what you can enable here and how you can change the settings here. As I said, this is now the normal mode without the advanced settings. I will show you later what is added when we enable this advanced mode. Kai already showed a slide of all the tools, of all the methods which are included in SIRIUS. And now we have them here already. Also a little bit changed. For example, in SIRIUS 5, you had an extra button for canopus, for the compound class prediction, which is now included in this predict properties in the middle. So it will be, most likely, it will be run for the computations you do. So of course you have to enable it, but you probably, for most tasks, you want to enable this button anyways. Okay, for SIRIUS, so for the molecular formula identification, especially because Kai said already we have all these different names for the methods. So here in this compute dialog, there's at least like a small description of what every method does. So SIRIUS is for the molecular formula identification. What you can select here, for example, is the instrument you use to measure the data. And this is like a profile, means now for QTOF we have MS2 accuracy of 10 ppm. And if we go, for example, to Orbitrap, it will change to 5. So this is just a profile which will be used. Then the other option you have here is this fixed formula for detected lipid. In SIRIUS, there's also lipid detection, like an extra tool which does not have any settings here, except for this one. But it will also be automatically run, and it might detect that the feature you're trying to annotate is a lipid, and it will even output the lipid class. And when it detects that your compound is a lipid, it will also detect the formula, the molecular formula of a lipid. And if this box is enabled, this means that if we detect a compound or a feature as a lipid, the formula of this lipid will be fixed. So the computations we do later on will only use this formula. We have also some fallback adducts to select here. So this really depends on the data you are loading into SIRIUS. For example, if you used mzmine before to get your data, you will probably also have some adduct assignments, and these will just be used. But SIRIUS, as we already showed, also has an adduct assignment. It does, an automatic adduct assignment. But if this adduct assignment fails, here you can select the fallback adducts, which will be used if we are not able to detect the adducts. And you can also enforce these fallback adducts to use even if we automatically detected the adduct.
Small question here. On the adducts, I quickly read through the list, and I see that there are only single charge states. For instance, the oral compound has +2 or +3 charge, which is not seldom in the nature of product score. How software handles this? What we can do?
So currently just support single charged because multiple charged probably fragment very differently. I don't know if we will support multiple charge in the future. I mean, for natural products, usually the mass of the compound is quite small, so probably the single charged is still the major ion type. But yeah, so currently it's not supported with multiple charged. So we will detect them, but we won't compute them currently.
Another question?
There's also the option to choose minus H2O, so minus water, which might be an in-source fragment.
Yes.
How is that distinguished? So M plus H and a possible in-source fragment of that.
I mean, it changes For the molecular formula notation, not much. It changes then the structured database search. If you look into the neutral formula or the neutral formula minus H2O. So we cannot, I mean, for the ADACT detection, it can distinguish them from the LCMS. Like you see there's a certain mass delta and the peaks correlate. Then you can assume, okay, it's probably an in-source fragmentation. The method also looks into the MSMS. So if you have two peaks, they correlate with each other, and the MSMS, the one is a subset of the other one, that's also a strong indication that this peak is an in-source of the other one. So that's all done automatically in the pre-processing. If you just have a peak list, there's no way to decide if it's an in-source or not, so you just have to provide that into the idea of the fallback ADACTs is exactly that you say, please consider this kind of ADACTs, and it will then compute data for all these ADACTs. If you now have M plus H and M plus H minus H2O, then there's no way to distinguish them. But if you then do a structured database search, it means it will look into both candidate lists. So
basically, when you pre-process your data in a different software, MZ9, and then export to SIRIUS, the MGF format, there will not be the option anymore to distinguish. Because you lose MS1 information.
yeah, right, but you have then the ADACT detection in MC-MINE and should annotate them in the MGF file. So it's basically the same. So the fallback ADACTs here are basically what should happen if there's no ADACT annotation, which is still the case for most of the compounds. Like in most cases, you just don't see the ADACT, and you can then say, if I don't see an ADACT peak, I always assume M plus H. That's, I mean, a valid strategy. Or you say, I want to not miss anything, so I then choose M plus H, M plus potassium, M plus sodium. That's what's the default, and what I would always do, just use these three, then it will compute molecular formulas for all three ions and rank them based on the number of explained peaks and so on in the statistical model. Yeah, and then you can always, I mean, I would always just use these three as fallback ADACTs. And then there's this enforce button, which basically say overwrite the ADACTs. Basically, or not overwrite, more like add these things no matter if there's already an annotation. And that's basically used when you say, I don't totally trust the annotation which is already in there. Let's say I process data with MC-MINE, and it annotates them as M plus H, but I have the feeling, it could be also M plus potassium, maybe there's something wrong. Then I can click on this enforce button, and it would say, add these to the candidate list.
Thank you.
Okay. So the next setting I want to show, and this is also new in Series 6, is that there are now multiple options to do the molecular formula generation. So you can do it either completely de novo, which you will now have to select from this drop-down menu, which can be computationally intensive, especially for very large compounds. But now in Series 6, there's also the option to do a bottom-up search, which Kai's already talked about. And it is usually really fast. So what is selected by default, this de novo plus bottom-up, it will do de novo and also, but only for the compounds or for the features below this mass, which is in this option. So below this option, we have perform de novo below MZ, and then you can select something here. So for these features, we will always perform de novo for molecular formula generation, but for the ones which are larger, there will only be bottom-up molecular formula generation performed, but also, which is important and where this element filter comes in, we will also do the bottom-up molecular formula generation for compounds below this threshold, because what the de novo search does is that we have specific elements which are enabled. You can change these here on the right side. So there's this element filter. And by default, we have, of course, the standard elements, CH, NOP. And there are also some elements which can be auto-detected. You even have the option to click on this dot 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 button and select more elements. If you, for example, know that you should have a compound in your sample somewhere with, for example, for example, if you have, you have like fluorine in your compound, you might want to go to this slider for F and select something here. What is important here is so the slider actually goes to infinity. So if you pull it all the way to the right, you will have inf standing here, which means, it can consider the possibilities for any number of fluorine atoms, and it can increase the computational cost by a lot. So if you use this, you should probably select like a reasonable upper limit for this auto detection. You can also select additional elements if you really want to here. As I said, by default, this filter is only applied to the de novo molecular formula generation, meaning you can still find many compounds which have other elements by this bottom-up search. But if you really want to restrict your molecular formula generation to some specific elements, you can change the option here to apply the filter also to bottom-up. And I think in SIRIUS 5, there were more settings for the database search, which is also now here in this drop-down menu, where you can just use any structured database and just be able to predict or annotate formulas which are present in these structured databases. But in most cases, this is the recommended setting to just leave it as de novo and bottom-up.
Maybe just a few words about the new bottom-up search. So it's based on the Buddy paper. And the idea there is that, we know that our structured database are not complete, and there are also a lot of molecular formulas missing. But if you now say, let's say, take a structured database and also consider a lot of biotransformations or neutral losses and extend the database this way, then we can assume that we probably consider 99% or even 99.99% of the molecular formulas. And that's basically the idea here. These bottom-up search do something like the database search, but it searches in a convoluted database consisting not only of molecular formulas from a structured database, but also apply biotransformations and neutral losses to them. And the problem with the de novo search is just really that it gets really slow at high masses. Like if you do de novo for 1,000 Dalton or 2,000 Dalton, then you often get millions of molecular formula candidates, and it will take just hours or even days then to compute them. And the bottom-up search basically breaks that down. It's really then also just takes seconds on large mass compounds usually, which means that in contrast to SIRIUS 5, you can really now process a complete LCMS run also with the high mass compounds, like with 1,000 Dalton in reasonable time. And so I would say de novo plus bottom-up is the recommended way to compute molecular formulas.
Zurich, we already talked about this and about this pop-up you get when you select it. Because here we just have selected 6 features, which is a very low number. So probably here it would not make sense. The next thing, which I also mentioned very briefly, is that we can now predict fingerprints and properties in general. So I said already that now Canopus is included in this box here. So if we turn it on, there's not many settings you can select here in this basic mode. What is toggled on by default is that because here we can get really many molecular formula candidates from SIRIUS, we only use the top scoring molecular formulas to predict molecular properties. Sometimes it might be the case that you maybe have good molecular formula annotations, but you don't have any good structure hits. And sometimes it can be a good idea to then toggle off this button, so it will do the predictions for all the molecular formulas. But by default, if you also don't want to have too much runtime, it's probably a good idea to leave this option on. So also, Kai said it in his talk, there's a part of the whole SIRIUS suite which does de novo computations, and we also do database searches, structured database searches, and everything we did up to now, so SIRIUS, Zodiac, if we toggled it on, and the predict properties is all de novo, so we can also get hits which are not in any structured database. But usually you want to have, or in many cases, you want to have very specific structure hits, and to do this, we now toggle on CSI finger ID, structure database search. And the most important part here is that on the right side, we have this menu where we can select all the databases, all the structured databases which we search in. What you will have later, when I've shown you the custom databases, you will also have the option to search in your custom databases. So, for example, if you have structures which might not be contained in PubChem or in any other structure library, you will also be able to search these custom structure databases here. There's also buttons at the bottom, all, none, and bio. All just turns on everything. None, for example, if you want to deselect everything to only use, for example, your custom database. And bio, which automatically selects all the databases which are part of our bio structure database. And what is new now in SIRIUS 6 is that often it was the case when you ran SIRIUS that you search for hits in the bio structure databases and you couldn't find something, you couldn't find your structure. And then often people rerun the computation and then searched in PubChem. So it's usually, or in many cases, you don't want to use PubChem already in the beginning. But what you have now in SIRIUS 6 is that if we have not found any good hits in our structured databases which we have selected, we can use PubChem as a fallback. And I might be able to show you an example also how it looks like, because you will also then have a box which says that in fallback mode, we also search in PubChem.
I just want to emphasize, because I think it's really a small feature, but it's really an important feature, because it's fully automated check if the top hits you get when you search in a bio database makes sense or not. And if it doesn't make sense, it then switches to PubChem automatically. And I mean, that's something everyone does if you really want to do annotation, like in CASMI, I think it was in CASMI 2022, I think. It was the key thing we did to get these good results. First search in bio databases and only search in PubChem if you don't find a good hit in a bio database. And I think it's really big thing that it's now automated, this process.
What we also have here, which was also added in SIRIUS 6, which Kai already talked about, is that we can now turn or switch the confidence mode, the confidence score, to approximate mode, which also, I will show an example to make this a little bit clearer, also considers structures or considers very similar structures to assign the confidence. I will show you an example to make it more clear. But here you would be able to switch between approximate and exact, but you can also do this in the main window. You don't have to do it in a computation. I will show it later. What we also have here now is new button for MS Novelist for de novo structure generation. Also, if you click on this, you will have a pop-up which shows that you still should be careful with the de novo predictions of structures. Also, what is important is that the runtime increases if you do it really for every compound. So it might be a good idea to just run it for some specific compound.
And it's also, I mean, as Fleming said, the project space can get quite large, but it's really the candidate list which make the project space large. So if you import MCML files, the project space is quite small. So it's often not as big as the MCML files even. But if you then run CSI finger ID, it gets quite large, and it's just because, I mean, you search in a structured database with millions of compounds, and they contain metadata, they contain fingerprints, and this stuff is all stored in the project space. And if you now also do MS Novelist, then you usually have 50 more candidates per molecular formula, which sums up a lot over a complete project space. So it can make really your project space a few gigabytes larger. So it's recommended to not use MS Novelist on all compounds, but really on purpose if you think that a certain compound you're interested in is not correctly annotated or is not contained in PubChem or any other structured database.
Yeah, so let's just turn it off for now. And this was also all the methods we can turn and toggle off here. What I said already, there is the advanced mode. And if you click on this at the bottom, you will see that now we have some more settings. I will not go into the detail here, but for example, if you see that your computations are taking a really long time, something that takes a long time to compute is the fragmentation tree computation. And maybe you might want to introduce like a timeout here. But yeah, in most cases, especially now because of the bottom-up search is fast, you should be good and should not be required to turn anything else here on. Also, we now see that we have now more options for Zodiac, but yeah, I will also not go into these options on detail. And
you should never touch them anyways. So yeah. There's a reason we hide them. Like, these are the options which are correct for the evaluation of the paper, and I think you should never change them.
So for most cases, really stick with the basic mode, which also has some settings. So you can, of course, it's not that you should really always use the default settings for everything, but you should at least not be required to change the advanced settings very often. What we might have to use later, if you have already done some computations and you changed something, you probably want to recompute with the new changes, and for this you have to make sure that this box at the bottom left is enabled, which recomputes already computed tasks. What is also very helpful in many cases is you have this button at the bottom which says show command. And this is like all the settings we now have. It seems very long, but this is only because also all the default settings are included here. So if you copy this command, for example, and run it in a terminal, you should get the same results, or at least you should have the same configuration. Yeah, and also one thing where it might be useful is if you find out, maybe you, for example, you have enabled Zodiac and you see that your laptop is not enough to handle it, especially if you have like an older laptop, but you have access to a compute cluster. It can be a good idea to first look at everything, import all your data, look at everything in the graphical user interface, then make the settings you want to do, and then just copy this command and of course your data and run it on a compute cluster, for example. So this can be very useful for this, and also if you just want to take note on what exactly you turned on, it's a good idea to just copy this and save it somewhere, just so you know in the future. Okay, now we are not going to click on compute now. You can try it out, but because we don't have infinitive time, let's just cancel. But what you would normally do is just click on compute and run all the computations. And what you would see is now, if you run the computations, that in the jobs pop-up, you would see the progress of all your computations. Yeah. But now first what I want to show you just very quickly is if you've done some computations, now at least it's a very good idea to save your project space somewhere. So just click on Save As. Yeah, just make a new folder, just save it somewhere. I will not show it now, but often it's a very good idea. And you would see that on the menu bar at the top, you would now then see the new project space location. Okay, what we are going to do instead is we are going to load the pre-computed results, which you have all downloaded. And to do this, we just use the Open button. And now we have to navigate to the folder where you have the pre-computed files. And the file name should be, so if you are in the For Participants folder, you will have one file which is named tomato_small.serious, and this is the project space. I think this is also by far the largest file. So I hope everybody has downloaded this. Yeah, as Kai said already, it's now a different project space format than for Series 5. So you will not be able to just load in your Series 5 project spaces this way. Yeah, but let's just go ahead and open this. I hope it works for everybody. What it will ask you is if you want to open it in a new window, because we will only be working with these pre-computed results. Let's just click no, so it will just replace our current window. It takes a little bit of time, but not very long. I think it's very fast, considering it's 1.3 gigabytes to load in. And now we have everything that is pre-computed, and one difference you will see here, actually I have not explained this very much, but in the compound view, at the top, you have your compound name, your feature name. You have the ionization, which has been detected or was maybe detected before, for example, by MZMine. You have your precursor mass. You have the retention time in minutes. As I said already, this list is by default also ordered by retention time. And what is now new is that you have a confidence score. So now for the top structure hits, you will get a number which tells us how confident we are that this structure is actually the correct structure. And what is also a difference to Series 5 is now it will say, right to the confidence, it will say A in parentheses, which means that the approximate confidence score is 1. Again, I will show an example to make this a bit more clear. But what you could do if you just right-click anywhere in the compound list, at the very bottom of this context menu, you have the option to use the exact confidence score. And then now it turns to confidence in parentheses E. And you can just switch between the two modes. I will show you an example soon where there's actually a big difference. Okay, but now we can see a lot more stuff. Before we will go into the detail on all the views, let's just apply a little bit of filtering, because you will see we have 530 features, and we will definitely not be able to go through all of these here, but also in most of your analysis. Often it's a good idea to restrict what you have in your data even further, especially if you know exactly what you're looking for, or at least know a little bit of what you're looking for. Just as a quick example, I want to show you how to filter by MZ, by mass ranges. So just for this example, let's just say we want all the features which have a minimum MZ of 300 and a maximum MZ of 350. And we also do a little bit of filtering on the retention time and say we only want compounds with a retention time greater than 5 minutes. So just to let you know, it's here we are required to enter the retention time in seconds, not in minutes. Yeah, but otherwise we will just leave everything as is. Maybe we can also just, again, exclude all the lowest quality hits. Yeah, what is also a good idea is that we might only want to show compounds which actually have MS data. Yeah, Kai already talked about this. So to do this, we can use this option here. So just to go through everything a little bit at least, here you can select MZ ranges, retention time ranges, but also you can select confidence score ranges. For example, if you're only interested in compounds where we are very confident on the predictions, you can select some settings for your MS data, the quality settings I talked about already. Also here you can filter by specific elements. You can filter by molecular formula, precursor formula. You can also here select some adducts for the filtering. And you can select the structure database. I also showed this a little bit. Okay, let's just apply this filter. Now we have only 144 compounds in this view here, so at least quite a bit smaller. And what I also want to show you, again, by default, this is ordered by retention time, but maybe if we don't have much time, or if we are only interested in the most confident predictions, we can also order this by confidence, which we are going to do now. So just right-click anywhere and click on Order by Confidence. And then you will see that at the very top, you will get the feature with the structure hit that has the most or the best or the highest confidence score, in this case 1. Okay, and let's just use this feature as an example. It's not, if everybody has this feature already, it's nice because you can see exactly what I'm doing. Also, if you don't see this at the top, you can just search for this directly. You can just enter the last numbers of this feature to get it. So this would be 80482. Let's just enter this here, and then we will only find this compound in this feature in this view here. Okay, and let's just go through all the views now, finally. So, of course, we still have the LCMS view, which I talked about already. You will now have the list of the top 10 molecular formula candidates here. You will have, so the formulas themselves will be in this column. You will have the rank at the left. You will have the adduct. Zodiac, we did not run it on the pre-computed project space, so we always have not a number score here for Zodiac. You will have the SIRIUS score, which is the score by which the molecular formula candidates are actually ranked. So this is a very important score. And all the scores which are part of the SIRIUS score. So for example, the isotope score, which tells us how well our isotope pattern, or the measured isotope pattern matches with the isotope pattern that is expected by this particular molecular formula. To show this, we can now go to the spectra view, and in the drop-down menu, click on MS1 mirror plot. I hope most of you are able to follow along. If not, just raise your hand if there's any problem. Okay. And here we can now see at the top our measured MS1 spectrum with the isotope peaks, and we can see at the bottom our simulated isotope pattern. And for example, if we look at this, we can see the differences, the mass differences between the isotope peaks at the top and at the bottom. We can see the peaks and where the intensity should be and where it is, and we can see how well it fits. So for example, to select now a different, so you can, with this list with molecular formulas, you can just go through it and select any other molecular formula which is not the top formula. And here, for example, you can see, or if we just scroll through this list, we can see that it changes quite a bit by what we select. And this is also reflected in this isotope score. What we also have, and there the tree comes in, let's just go to the top formula again. We have a fragmentation tree. And what Kai already showed you in one slide is that if we go to the MS2 spectrum, we can just click of any of these green peaks. Green peaks means that we have a node in our fragmentation tree which corresponds to this peak, and we can just click on this, for example, and you will see that now the node in the fragmentation tree, the fragment here, which corresponds to this peak, will be selected, and you can look at it a little bit more and also see where it is in the fragmentation tree. Yeah, and you can just move through it if you want. Also, maybe a little bit of a pro tip, you can, for example, if you want to select a very small peak, this might be difficult with a mouse, although you can zoom in also. But what you can also do is just use the arrow keys on your keyboard to switch between the peaks. Okay. So what we also have, besides the isotope and tree score, is we can look at the number of peaks which are explained by this particular molecular formula and its fragmentation tree, which is here in this explained peaks column. We have the total explained intensity. So this means, for example, that 96% of the total intensity can be explained by this molecular formula. We also have some errors, which I'm not going to go into the detail here. And this last column is part of the lipid class detection.
I would say in general, so the explained intensity should be above, I would say, 0.8 usually for MS spectra. Otherwise, it's suspicious at least. Like, could be a noisy spectrum, it could be a chimeric spectrum. In this case, then the explained intensity can be lower. but you would expect that most peaks in your spectrum should be explained by the fragmentation tree. Otherwise, I wouldn't trust the molecular formula annotation.
Yeah, we'll also soon see an example where we probably shouldn't trust the formula. Okay, then the next step we are going to look at is the predicted fingerprints. So again, the formulas and the predicted fingerprints, this is still de novo. So here we are trying to see which properties belong to the data we have measured. And you now have a very long list of properties, and often if you want to look at this in more detail, it might be good to just search something, for example, or to filter this list a little bit. So just to explain this a little bit, you have the index of your substructure, you have the smarts, you have the posterior probability, which just means do we think that this probability is present given the data we have measured, the number of atoms, which we don't have for all the substructures, where we will have just undefined, then the type, and the positive training examples. But what also is important, the predictor quality, which means how should we really trust this predictor? I will show also an example for this. This just means if we have a high score here, this particular predictor is also trustworthy, and if we have a lower number, we should be careful. Okay, let's just filter this list a little bit and select, for example, only substructures which have like a probability of 0.3. I didn't show this, but if you would have scrolled down to the bottom, you would also see. So now this posterior probability, this list only goes to 30, and yeah, you can select, or you can see the probability, the substructures which are at least mostly be predicted to be present. What you can also do is filter by the number of heavy atoms. So often you get some substructures which are not really that interesting. For example, like 2 carbon atoms is not really something very useful. But if we say, for example, we want to have at least 6 heavy atoms, and we will now click on some of these structures, you will see, now in the bottom, you will see examples of how these substructures look like. And okay, so it looks like we expect something like this for our structure.
So in general, I would always make a filter over the probability and then click on the atoms column, because
you can also
this will sort the list based on the number of atoms,
Yeah.
and then go from top to down, because then you see the substructures which are quite meaningful because they are large, so you can get some information from them, and you can then scroll down the list and look at the large substructures which are contained in your molecule by high probability.
Yeah, especially here, if we go to the top ones, it will really give you some information on what we predict the structure should look like. And again, this is still de novo. And this also is true for the compound class prediction. So we also performed Canopus, which gives us predictions for the compound class, which we expect. And here it is important what I should maybe explain before. The list of molecular formulas, which was before just a normal vertical list, is now this horizontal list. So we can also go through other molecular formulas if we just select something else from this list. But what is important here is that first you have Canopus predicts 2 different kinds of classes, classifier classes and natural product classes. The classifier classes is what you have here at the top and here in the middle, and in the bottom you have the natural product classes, which are just 2 different types or 2 different methods to assign compound classes to compounds. What is important is that for natural product classes you always get a hierarchy, meaning you get one pathway, one superclass, one class, and so on. But for classifier, which makes a lot of sense, you also get many alternative classes. So your compound can not only belong to one kingdom, one superclass, one class, and one subclass, but you will see all the alternative classes here in the middle. And it's always a very good idea to also look at these alternative classes. And if you hover over this, you can see the probability, so you can see that also for all these alternative classes, we really predict them to be present.
So alternative doesn't mean it could be this or this, but it really means it's both. Like a compound class in the sense of classifier is basically some kind of substructure. Like something can be a steroid and also a bioacid, because a bioacid has a steroid substructure in it. So it is both then. That's basically ideal.
Yeah. You can also, here, I will not go into the detail on this list, but you can also search this list if you want, if you are looking, for example, for a specific class and you want to see how the posterior probability for this specific class is. Now let's go to the structures, which are a question, yeah?
The result that we obtain using high-throughput is the same always, because I have to mention that in the past, using SIRIUS 5, we noticed that it is different for the same compound, the classification that's assigned for my partner and for mine. Well, very similar, but not the same as when we did subclass or level 5, the assignment was not the same.
Should be the same on exactly the same data. At least in SIRIUS 5 and SIRIUS 6, of course, new versions or predictor changed. But if you process this exactly same spectrum, it's a deterministic process, it should be the same.
What is maybe very important to mention here is, especially now that we are going over some specific structures, now we are not anymore in the de novo part. So we are now looking for hits in structure databases. But what is very important is this does not correspond, so the structures we have here don't correspond necessarily to the compound classes we have predicted. The compound class prediction is still de novo. So it's often a good idea if we now look at specific structure hits to see if the compound classes also fit the compound classes that we have predicted. Especially now that I'm showing all these different kind of views, it's maybe important that usually if you run SIRIUS, you are not only looking for only one score or one very specific thing, but you have really many things, very different views to look at your data, and they can all give you indications on what might be the correct structure or what might be correct information on what you have measured. So it's always, you should always really keep in mind that you have all these different sources of information, and also to not predict, to not believe like every single score, but to look at different things and just see how they fit all together. I think this is very important also as a little bit of a take-home message. So let's go into the structure tab now in detail. Now we have our top structure hits. The top hit is colored in green. And we will have the name of the structure here at the very top. The names, sometimes these are the UPAC names, sometimes these are like more common names for compounds. But often it's a good idea, because we only display one name, and of course compounds can have different names. It's a good idea often to go to some database where the structure was found, just to see more information, but also to maybe get some other compound names. For example, if you are looking for a very specific compound and you don't see the name here, it might just be that it is named differently here. And yeah, this also brings us to, of course, here in the middle we have the structure, but this also brings us to the sources, and these are the databases, the structure databases, where this particular structure was found. So in this example, Coconut, PubChem, and Supernatural. Let's just click on Coconut here. You can just click on these boxes, and it will open now new windows in your browser. I hope it doesn't take so long. Okay, seems to work. Now we are in the Coconut database, and we can look through all the information here. And for example, what we can now see here, if we scroll down in Coconut, they also have chemical classes annotated here, classifier classes, and you see that this particular structure is in classifier is a cinnamic acid amide. And if we go back to the compound classes tab, you see, this is also what Kai mentioned, you will see the cinnamic acid amide here as an alternative class. So really, again, to emphasize this, alternative does not mean that it's like a verse prediction. It just means that there are multiple classes that a compound can belong to, and these classes are also just as correct as the ones at the top. Yeah, we have to be a little bit faster probably now. Okay, so just one thing to highlight here. In the middle we have the substructures from our predicted fingerprints tab, but now the posterior probability, which for this structure is not really high, but the posterior probability is now the color of the box. So if we go back to the structures, a blue box means that the structure we have predicted it to be present. So if you hover over it, you see the smarts of the substructure, and you see that it has a 100% posterior probability. And so these are only the substructures which are present in this structure hit. So this is, so if we can just click on something and it will be highlighted here. The red boxes mean that we predict it to not be present. So for example, this part. And the size of the box, for example, this very tiny box means that the predictor quality is not very high. So you should probably not trust it that much. What you can also do here is right-click on the compound and click on highlight matching substructures. And this way you will get a little bit of an overview. You will see which parts match, which don't. Yeah. Okay, now to the next step. Actually, this will look exactly the same because the tab is named de novo structures, and it is meant for the MS Novelist hits. But by default, we have this little button here active, which says show the MS Novelist results and the CSI finger ID results together. If we would turn it off, we would see that we don't have any results here. So we have not run MS Novelist for this particular compound. We can, for example, run it now, but because it takes a little bit of time, I'm just going to skip this. Kai already had a slide where he showed how the hits in MS Novelist look like. You just get a list which looks very similar to the structure hit, but then you will see that the source for this structure hit will be de novo. So it was predicted by MS Novelist. Okay, substructure annotations can also be really helpful if we want to see if we now have like a structure hit that we maybe trust already or think that is a good hit, and we want to see how does it actually fit to the MS2 spectrum we measured. So what is also important here, we can just take any structure hit, and for any structure hit, it will try to assign the peaks in the MS2 spectra to this particular structure and to substructures of the structure. The peaks where we have such a match will be purple, and you can just click on them, and on the right you will see which part of the structure was annotated for this particular peak. And you can just go through everything and see if it makes sense for you, especially if you have more knowledge on this. You will also see some other information here in this list, but I'm not going to go into there in detail. But again, it's always a good idea to just look at this tab.
So basically that's a combinatorial fragmenter like MedFrag built in, which shows you just another view on the data based on can I fragment a molecule into parts that fit into my peaks? And hopefully most of the peaks should be purple, then it's a good sign that the fragmentation makes sense. There's an annotation.
Okay, the next step would be the library matches, which we showed already in the slides. That is now possible to see if we have actually a hit in a reference spectrum database. For this particular compound, we don't have any match, but I will show you soon an example where we have a match. Okay, so now we went through everything, or mostly everything. Let's now clear the filter and look at some other examples. For example, now we are looking for a compound which has the mass of 578. So now we are filtering by mass, and we're looking for 578. We can just type it here and a dot, so it only gives us the masses and doesn't search in the compound name. Okay, this might also happen to you that you don't have any thing in your compound list. So this is because we excluded something before. So let's click on the filter button again, click here on reset to reset the filter and apply. And now nothing is filtered, and we will be able to just type it here. And now we'll see we have here a compound which has, let's go back to just the SEMS view, which has the mass of 578.40 Dalton. I hope some of you, or many of you, hopefully also seeing this compound. And I'm not going to go through everything again, of course, but what we can show here is if we go to the structure tab, we see that we seem to have a very good hit, or at least a hit, which seems to have a high score. So this is the CSI finger ID score, which is negative. So minus 70 is, I think, a pretty high score. We see that also the substructures, we have many blue boxes here, they seem to fit. And what is very new and what I want to show here is that we not only have sources here from the normal structure databases like PubChem, Lotus, and so on, but we also have a hit in something else. And this is a custom database which we have created and which we have run again. So you can, as I said already, you can search also in your own custom structure databases if you want. Just to show you how you would do this, we have this databases tab here. It should be empty if you have not created any custom databases. But what you can do here is you can either load a custom database which you have saved already, which you do by this button here, add existing database, or you can create your own custom database and, for example, just use some smiles, so just some structure representations to make your own custom database to search in. For everybody who has downloaded the new folder from the Google Drive, you should be able to, let me close this again, you should be able to click on this button and click on Add Existing. And now you should be able to navigate to wherever you downloaded everything. And here in this new folder, there will be a file named tomatidine SIRIUS-DB, which will be the custom database which we have created already. Just because we don't have so much more time, I will just go through everything. So if you don't follow along, probably try to look at what I'm doing, and yeah, let's just see how far we come. So let's just open this database, and now it is imported, or it is loaded in this case. And now we would be able to search in this structure database. Before, I want to show just one very quick thing, especially because I mentioned the thing about the name here. You have this very, very long name here, this UPEG name for this best structure hit. And for example, if you click on Lotus, which is also it's a database which contains, for example, information on the species where this data has been measured in already. Okay, doesn't seem to load now.
Just one comment to the custom databases. That's also the tab where you can import your in-house spectral libraries. Yeah. And I think we also have in the have an MSP file, so this mass bank spectral record format or list format, and you can just drag and drop that in the custom database dialog to import, for example, mass bank. It also accepts MGF files, so you could also import GNPS, for example, this way. Yeah, that would be the way how you import your custom database basically over this tab. So we don't make a difference internally between structured database and spectral databases.
Okay, because we don't have so much more time, I'm not going to wait on this, but what you could see on Lotus is, okay, I can show it. So what you can see here, you have measured this in these species, and if you know more about biology than me, you know that this solanum is nightshades, which fits very well to the data we have, which was measured in tomato plants. And also, we named our custom database tomatidine. So, yeah, we are expecting some tomato compounds here, which we have apparently found. Yeah, okay. So, and if you click on PubChem, you could see that one of the structures we get in PubChem also has the name tomatidine and then something else. So it is seems to be some modification of tomatidine, what we have found here, which is with a very good hit. Okay, now that we have opened this custom structured database, we can also filter by this database. Just to show it very quickly, we now have here hit in StructureDB. We have tomatidine, which is the database we just opened. And if we enable this and click on apply, it will now only show us features which have a structure hit, which is contained in this custom structure database, which are not a lot because it was also a very small database. One feature I want to show very quickly is, let me see. Yeah, is this one. This is named tomatidine, so we really expect this here. And what I will not show you very much here, but actually we had a hit in our reference spectral library. So we used MassBank. This is, as Kai said, the MGF file you downloaded. And here we had a good hit in MassBank. Because we have not opened the custom database here, I cannot show you the mirror plot of the MS2, but we can still see our list of hits and can see the similarity and so on. Okay, some other very quick examples. There are some things or some compounds where you should be a little bit cautious when you see it. Just to show this very quickly, I will just so you don't have to follow along. I will just enter now some of the feature numbers I wanted to show. So if we go to this, for example. Okay, this is something which is actually quite interesting, but it's hard to show it in a short time. What you can see here, that the structure doesn't seem very good. You have many substructures which don't match. And what I'm not going to explain in detail here, but what you could see is that it's very, let's go back to the fragmentation tree. You will see if you zoom in here that there seems to be a loss which contains 3 C atoms and 5 N atoms, nitrogen atoms. And you will see that this is impossible with this particular structure. It's impossible that you have a loss like this where only 3 C atoms fall off, but 5 N atoms. So again, always look through all the different views.
I mean, it would consider really heavy rearrangements to let all the nitrogens cleave off and not offer atoms. So that's really unlikely.
Okay. Let's go to some other examples where you should be a little bit careful. Yeah, so this is what can also happen. Here you just have a very empty MS2 spectrum. So probably we will not able to extract much information from this. Also another example where you should be careful. Here you will see what Kai mentioned already. You have only 3 explained peaks and only 24% of the total intensity can be explained. So also here you should be very, very careful. Probably you won't analyze it any further because this just doesn't seem to be a good molecular formula candidate. Okay, and then what I really wanted to show you is an example where we can show the difference between the 2 confidence core modes. So we are now in the approximate confidence mode. So we have here confidence in parentheses A. And if we go to the structures, we can actually see that now 3 structures are highlighted. And this means that all these structures are very similar and have an MCS distance, if you are interested in the details, of not greater than 2, which means that basically to get from one molecular graph to the other, you would need to delete fewer than or equal 2 edges. So these are very similar. And if we go back to what we had before in SIRIUS 5, the exact confidence mode, you will now see that first the confidence is much lower. We only have 0.5 instead of 0.7, and you will only get 1 hit because this confidence mode only considers the top structure and not structures which are very similar to the top structure.
basically historically, I mean, the confidence score was introduced to tell you the likelihood that the structure annotation hit is correct. But what we found then was that quite often we have candidate lists where the top 3 candidates were just indistinguishable. Like there's only one OH group moving in a ring at some position, and it's probably even impossible with mass spec to distinguish them. Like they would have the same MS spectrum. But still, if we know that one of them is correct, that's also a lot of information. But if we then sort them by confidence, they would have a really low confidence and would go down in the list. And so if you sort your list by confidence score, you would miss these candidates where the correct answer is known, but you cannot distinguish between 2 super similar structures. So that's why we now have this approximate mode, which just means we are confident that our annotation is correct, but we cannot distinguish the top 2 answers, for example.
Okay, just because we're running out of time, just want to prepare something very quick. But before, just one thing I want to show. We talked a little bit about this lipid class prediction. And this is how it looks like when we have actually predicted a lipid here. You can see here, El Gordo, which is the name of the method, has predicted this feature to be a lipid. And it has predicted it with this particular lipid class. And here we can also see that this lipid class matches our top structure. So the structures we find are not necessarily have to correspond to what El Gordo predicts, but here it is the case. Okay, and also just very quickly, you can export everything in this write export summary TSV files. So very important if you want to export everything, to analyze it in a different tool, to make some statistics and this kind of stuff. And very, very quickly, the API, which Kai already talked about. And it's very, so first of all, you can also, there's also, I hope it works already, but there should be a Python and an R client to access the API. But you can also do everything in the browser if you want to. You can pretty much do everything you can do in the GUI, also now in the browser. And just, if you know this a little bit, you can just write your own requests, for example, open up a new project space. You would just go here, and you can click on the try it out button, and then you can, for example, just specify the path to your project space and load it in. And you can pretty much do everything, like all the actions you did in the GUI, you can also use it programmatically. And also, for example, you can get the spectra, which SIRIUS has this way. Yeah, just to highlight this very quickly. But now we are out of time. But if there are questions, definitely feel free to come up to us, to ask us anything. Also, we have some very nice stickers for SIRIUS, if anybody wants to have a sticker on their laptop. Yeah, thank you.
Probably have to leave the room soon, but feel free also to ask us any questions during the conference. If you need any help or have any questions about SIRIUS.